Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, adjust your pillow, let your body sink a little deeper into wherever you're resting. There's nothing you need to do but listen. Where in the world are you watching from? A quiet bedroom where the evening has finally settled? A cosy corner where the day's noise has faded away? Wherever you are, you're welcome here. Tonight we're going to explore something quite remarkable. A visitor from interstellar space that arrived in our solar system and sparked one of the most fascinating debates in modern astronomy. We'll discover what made this object so unusual, understand why scientists can't agree on what it actually is, and contemplate what it means when something from beyond our solar neighbourhood comes to call. This is the story of 3I/ATLAS, an object that defied easy categorization and reminded us how much we still have to learn about the universe. But don't worry, this isn't going to be a tale of cosmic doom or alarming revelations. Instead, we'll move slowly and carefully through the observations, the theories, and the beautiful disagreements that make science work. By the end, I think you'll find that uncertainty can be just as fascinating as certainty, and that not knowing everything is part of what makes discovery so profound. If you enjoy these calm explorations of space and science, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this quiet community. So settle in, let your shoulders drop, take a slow breath, and let's begin our slow drift through the story of a mysterious visitor from between the stars. There's nowhere you need to be. Just listen and let the story unfold. The universe can wait. Tonight, we have time. On the 19th of November 2020, a telescope in Hawaii detected something new. The Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System, was doing what it does every clear night, scanning the sky for objects that might pose a threat to Earth. But this particular detection was different. The object was moving, as expected, but it was moving in a way that suggested it hadn't originated in our solar system. The discovery was made at the Mauna Loa Observatory, high on the slopes of a dormant volcano, where the air is thin and the stars are brilliantly clear. Atlas uses relatively small telescopes, just 0.5 metre across, but what it lacks in size it makes up for in coverage. It scans the entire visible sky every night, processing millions of data points, looking for anything that moves or changes. Most of what it finds are asteroids, comets, and satellites. But occasionally, very occasionally, it finds something that doesn't quite fit the pattern. This object was given a provisional designation, a /2020 V2. The A stands for asteroid, though that classification would soon become questionable. The numbers and letters that follow are simply a cataloguing system, a way to mark when and where in the sky it was found. But within weeks, as more observations came in and astronomers calculated its trajectory, the designation changed. It became C/2020 V2, with the C standing for comet, and then, finally, it received the name that would stick, 3I/ATLAS. The 3I is particularly significant. The I stands for interstellar, and the 3 means it's the third interstellar object ever confirmed to visit our solar system. The first was Oumuamua, discovered in 2017. The second was 2I/Borisov, found in 2019, and now this, 3I/ATLAS, the third visitor from the space between the stars. What makes an object interstellar? It comes down to speed and trajectory. Everything in our solar system orbits the sun in elliptical paths bound by gravity. Even the most eccentric comets, those with orbits that take them far beyond Neptune, are still gravitationally tied to our star. They go out and they come back. But an interstellar object is different. It's moving so fast and on such a trajectory that the sun's gravity cannot hold it. It comes from somewhere else, swings through our neighbourhood, and then leaves, never to return. when astronomers calculated the orbit of 3I/ATLAS, they found exactly this pattern. The object was moving at roughly 34 kilometers per second relative to the Sun. That might not sound extraordinary, but when you factor in the Sun's own motion through the galaxy and account for the gravitational influence of the planets, the mathematics revealed something clear. This object was not bound to our solar system. It had come from interstellar space, and it would return there. But where had it come from? And more puzzlingly, what exactly was it? These questions would spark debates that continue to this day, because 3I/ATLAS didn't behave quite like an asteroid. And it didn't behave quite like a comet either. It was something in between, or perhaps something else entirely. And in that ambiguity lies a story worth exploring slowly. To understand why 3I/ATLAS caused such confusion, we need to understand what astronomers expect from objects in space. For most of history, we thought we had it figured out. There were stars, which are massive balls of fusing hydrogen. There were planets, which orbit stars and don't produce their own light. There were moons, which orbit planets. And then there were the small bodies, asteroids and comets. Asteroids, in the traditional view, are rocky or metallic objects, leftover debris from the formation of the solar system. They're mostly found in the asteroid belt between Mars and Jupiter, though some wander into the inner solar system. They don't have atmospheres, and they don't change much as they move through space. They're inert, ancient, cold. Comets, on the other hand, are different. They're often described as dirty snowballs, mixtures of ice and rock and dust. When a comet gets close to the Sun, the ice begins to sublimate, turning directly from solid to gas without becoming liquid first. This creates a glowing atmosphere around the comet called a coma, and often a tail that streams away from the Sun, pushed by solar wind and radiation pressure. Comets are active. They change. They're dramatic. This binary classification worked well for a long time. If you saw a fuzzy object with a tail, it was a comet. If you saw a sharp point of light that didn't fuzz up, it was an asteroid. Simple enough. But nature, as it turns out, doesn't always respect our categories. In recent decades, astronomers have discovered objects that blur the line. There are active asteroids that release dust but don't quite look like comets. There are dormant comets that have lost most of their ice and now look like asteroids. There are objects that seem to switch back and forth, becoming active for a while and then going quiet. The universe, it seems, enjoys challenging our neat classifications. When Oumuamua arrived in 2017, it challenged these categories in a new way. It showed no signs of cometary activity, no coma, no tail, but it accelerated slightly as it moved away from the Sun, as if something was pushing it. The most likely explanation was outgassing, the release of gas from ices on its surface, but the gas itself was never detected. This led to all sorts of speculation, some of it quite exotic. The object became famous partly for what it might be and partly for what we couldn't quite explain. 2I Borisov, the second interstellar visitor, was more conventional. It looked like a comet, acted like a comet, and everyone agreed it was a comet. It had a bright coma. It released gas that could be detected and measured, and its composition seemed similar to comets from our own solar system. This was reassuring. The universe, it seemed, made sense after all. And then came 3I/ATLAS, and suddenly the debates that had surrounded Oumuamua came roaring back, because this new visitor didn't fit neatly into either category. It wasn't quite a comet, and it wasn't quite an asteroid. Or perhaps it was both. Or perhaps it was something we hadn't properly defined yet. And that's where the arguments began. Let's explore what made this object so confusing, and why smart people with the same data can look at it and come to entirely different conclusions. After Atlas detected the object in November of 2020, astronomers around the world turned their telescopes toward it. This is standard procedure when something unusual is found. The more observations you have from different locations and different instruments, the better you can understand what you're looking at. and everyone wanted to understand this new interstellar visitor. The first thing they measured was brightness. How much sunlight was the object reflecting? This is measured in magnitudes, an ancient system that astronomers still use where smaller numbers mean brighter objects. When first detected, 3I/ATLAS was around magnitude 19, which is very faint. Far too dim to see with the naked eye. You'd need a decent telescope and dark skies. But as the object moved closer to the Sun over the following weeks, it brightened, eventually reaching magnitude 16 or 17 at its peak. Brightness tells you something about size, though it's not straightforward. A small, bright object can look the same as a large, dark object. You need to know the albedo, the reflectivity of the surface. Is it shiny like ice, or dark like charcoal? Most asteroids have low albedos, reflecting only a small percentage of sunlight. Comets can be brighter because of their dust and ice. Based on the brightness of 3I/ATLAS, and assuming a typical cometary albedo, astronomers estimated it was perhaps a few hundred meters across, not huge but not tiny either, about the length of 3 or 4 football fields. The next thing they looked for was a coma. Was there any fuzziness around the object? Any sign that it was releasing gas or dust? This is where things got interesting. Some observations showed what might be a very faint, very small coma. The object wasn't a sharp point of light like a distant star. It seemed slightly extended, slightly fuzzy. But was this real activity, or was it just an optical effect, perhaps from the way the telescope was tracking the fast-moving object? Different teams reported different results. Some said yes, there's definitely a coma. It's small, but it's there. Others said no, we see a point source, there's no activity at all. And still others said it's ambiguous, we can't be sure. This disagreement wasn't because anyone was being careless. Observing faint, distant objects is genuinely difficult. Atmospheric conditions matter. Instrument sensitivity matters. The way you process the data matters. Two people can look at the same image and reasonably come to different conclusions. Then there was the question of spectroscopy. When you split the light from an object into its component colours, you can learn what it's made of. Different molecules absorb and emit light at specific wavelengths, creating a unique fingerprint. If 3I/ATLAS was a comet, you'd expect to see signatures of water vapour, carbon monoxide, carbon dioxide, maybe cyanogen or other organic compounds. These are the typical gases released by comets as they warm up. But detecting these gases is hard when the object is faint and far away. Several teams tried, using some of the most powerful spectrographs available. The results were, once again, ambiguous. Some thought they detected weak signatures of gas emission. Others found nothing conclusive. The signal-to-noise ratio, the measure of how much real signal you're getting versus random fluctuations, was just barely at the edge of what's detectable. It's like trying to hear a whisper in a noisy room. You think you heard something, but you can't be certain. All of this data, collected over weeks as the object moved through the inner solar system and then headed back out toward interstellar space, painted a picture that was frustratingly incomplete. There were hints of cometary activity, but nothing definitive. There were suggestions of a coma, but not everyone agreed it was real. The object was bright enough to study, but not bright enough to study easily, and so the debates intensified. What exactly was 3I/ATLAS? Let's consider the case for 3I/ATLAS being a comet. Many astronomers looked at the available evidence and concluded that yes, this is a comet, albeit an unusual one. Their reasoning was based on several key observations and inferences. First, there's the matter of the coma. While not everyone agreed on its presence, several independent observations from different telescopes suggested that the object had developed a small atmosphere of gas and dust. This coma appeared when the object was closest to the Sun, which is exactly when you'd expect a comet to become active. As the sunlight warms the surface, ices sublimate and gas begins to flow away from the nucleus. This is standard cometary behaviour. The images showing this potential coma weren't dramatic. There was no spectacular tail like you might see in pictures of famous comets like Hale-Bopp or Halley. But most comets aren't that dramatic. The vast majority are faint. Their comas barely perceptible even with professional equipment. The fact that 3I/ATLAS might have a small weak coma doesn't disqualify it from being a comet. It might simply be a small comet, or one that's relatively depleted of volatile materials. Second, there's the trajectory and behaviour as the object approached and then receded from the Sun. Some observations suggested that 3I/ATLAS might have experienced a slight non-gravitational acceleration, a tiny push that altered its trajectory in ways that gravity alone couldn't explain. This is a hallmark of cometary activity. When gas jets away from one side of a spinning comet nucleus, it acts like a tiny rocket engine, gently pushing the comet in the opposite direction. This effect, called the rocket effect or outgassing force, has been observed in many comets. The evidence for this acceleration in 3I/ATLAS was not overwhelming. The effect, if it existed, was small, perhaps at the limit of what could be detected given the uncertainties in the observations. But several researchers who analysed the orbital data concluded that yes, there was a slight deviation from a purely gravitational orbit, and the most likely explanation was outgassing. Third, there's the question of composition. While spectroscopic detection of gases was inconclusive, some researchers pointed to the overall colour and reflectivity of the object as evidence for a cometary nature. The light curve, how the brightness changed over time, suggested a surface that might be a mixture of dark dust and brighter ice patches. This is consistent with cometary nuclei, which are often described as having heterogeneous surfaces. Moreover, the fact that 3I/ATLAS is an interstellar object actually makes the comet hypothesis more plausible in some ways. Comets in our solar system spend most of their time in the cold outer reaches, where ices can remain stable for billions of years. An interstellar comet travelling through the even colder environment of interstellar space would be preserved in a pristine, frozen state. Such an object might still contain the original ices from whatever planetary system it formed in. When it finally encounters a star, ours or any other, those ancient ices would begin to sublimate. The comet hypothesis also makes sense from a population standpoint. There's reason to believe that comets might be ejected from planetary systems more easily than asteroids. During the formation of a solar system, gravitational interactions with giant planets can fling icy bodies out into interstellar space. These exiled comets would wander the galaxy, and occasionally one would pass through another star system. If this process is common, then interstellar space might be filled with rogue comets, and we should expect to see them occasionally. So the case for 3I/ATLAS being a comet rests on this combination of evidence: a possible coma, potential non-gravitational acceleration, composition and colour consistent with icy bodies, and the theoretical expectation that interstellar comets should exist. It's a reasonable position, supported by data, even if that data is not entirely conclusive. But science thrives on skepticism, and not everyone was convinced. Now let's consider the other side of the debate. A significant number of astronomers looked at the same data and concluded that no, 3I/ATLAS is probably not a comet. It's more likely a rocky asteroid, or at least an object with very little ice. Their arguments are equally compelling. First, there's the issue of just how faint and ambiguous the coma was. If 3I/ATLAS were a typical comet, you'd expect more obvious activity. Comets are usually quite noticeable when they get close to the Sun. They brighten dramatically. They develop extensive comas. They often grow tails that can stretch for millions of kilometres. But 3I/ATLAS did none of this in a clear, unambiguous way. The alleged coma was so faint that multiple teams couldn't even confirm it existed. To some researchers, this suggested that either there was no coma at all, or the activity was so weak that it barely qualified as cometary. There's also the question of gas detection. Spectroscopic observations are the gold standard for identifying comets. If you can directly measure the gas coming off the object, you have definitive proof of cometary activity. But despite efforts by skilled observers using sensitive instruments, no one could conclusively detect the signature gases you'd expect from a comet. There were hints, maybes, possibles, but nothing certain. And in science, absence of evidence, while not evidence of absence, is still noteworthy. Some researchers argued that if 3I/ATLAS were releasing gas, we should have been able to detect it. The object wasn't that far away during its closest approach to the Sun. We had the technology and the telescopes. The fact that we didn't see clear gas signatures might mean there wasn't much gas to see. And if there's no gas, it's hard to call something a comet in the traditional sense. The supposed non-gravitational acceleration was also questioned. Orbital calculations are complex, and small uncertainties in measurements can lead to different conclusions. Some teams, recalculating the orbit with their own methods and assumptions, found no significant deviation from a purely gravitational trajectory. They argued that any apparent acceleration was within the margin of error, an artifact of measurement uncertainty rather than real physical phenomenon. Moreover, there's a phenomenon called the Yarkovsky effect that can cause non-gravitational acceleration in asteroids without any outgassing. This effect occurs when an asteroid absorbs sunlight on its day side and re-radiates that energy as heat on its night side. Because the night side is rotating away from the Sun, this asymmetric thermal emission creates a tiny thrust. Over time, this can measurably change an asteroid's orbit. Could the Yarkovsky effect explain any orbital anomalies in 3I/ATLAS without requiring cometary activity? Some researchers thought yes. There's also the broader context of Oumuamua to consider. The first interstellar object sparked enormous debate precisely because it showed possible non-gravitational acceleration without clear evidence of outgassing. Many researchers were skeptical of exotic explanations and preferred to see it as a comet with very low activity or an unusual surface. When 3I/ATLAS came along with similar ambiguities, some astronomers worried that we were jumping to conclusions again, seeing comets where there might be none. The asteroid hypothesis also has theoretical support. While it's true that comets might be more easily ejected from planetary systems, asteroids can be ejected too. Close encounters with planets, stellar flybys, or even the complex gravitational dynamics of binary star systems can fling rocky objects into interstellar space. If interstellar asteroids exist, and there's every reason to think they do, then 3I/ATLAS could be one of them. Finally, there's a philosophical argument. Science should be conservative in its claims. Given the ambiguous nature of the observations, should we really classify this as a comet? Or should we acknowledge that we simply don't have enough information? Some researchers preferred to call 3I/ATLAS an interstellar object, full stop, without committing to a specific type. This captures the uncertainty honestly. And so the debate continues, with intelligent people on both sides, each looking at the data through their own lens of experience and interpretation. Let's slow down and think carefully about what we can actually see when we observe something like 3I/ATLAS. Astronomy is fundamentally about collecting light. We point our telescopes at distant objects and gather photons, individual particles of light that have travelled across space. From those photons, we try to reconstruct reality. When you look at an image of a distant asteroid or comet, you're not seeing the object itself in the way you see a bird or a tree. You're seeing a pattern of light that has been captured by a detector. For bright objects, like the planets, we can resolve actual features. We can see Jupiter's bands and Saturn's rings, but for small distant objects we see only a point of light, or perhaps a slightly smudged point. The question of whether 3I/ATLAS had a coma came down to this. Was the light distributed in a tight star-like point, or was it spread out over a larger area? This is measured using something called the point spread function, which describes how light from a point source gets spread out by the telescope and atmosphere. A star, which is effectively a perfect point source because of its enormous distance, has a characteristic spread pattern. If an object appears more extended than this pattern, it suggests the object itself is extended, perhaps with a surrounding cloud of dust. Several research teams analysed images of 3I/ATLAS using this technique. They compared the object's appearance to nearby stars in the same images. Some found that yes, 3I/ATLAS was slightly more extended than the stars. The difference was small, perhaps only 10 or 20% more spread out, but it was there. They interpreted this as evidence of a coma. Others, using different images or different processing techniques, found no such extension. To them, 3I/ATLAS looked like a point source, indistinguishable from a star. They suggested that the apparent extension reported by other teams might be due to tracking errors. When you photograph a moving object, you have to adjust your telescope to follow it across the sky. If the tracking is slightly off, the object can appear smudged in the image, mimicking a coma. This disagreement highlights a fundamental challenge in astronomy. We're working at the very edge of what our instruments can detect. When a signal is just barely above the noise, interpretation becomes crucial. Two experts can look at the same data and come to different conclusions based on how they process and analyse it. Neither is necessarily wrong. They're both doing their best to extract truth from limited information. There's also the issue of temporal changes. Some images were taken early in the observation period when 3I/ATLAS was still relatively far from the Sun. Others were taken near perihelion, the closest point to the Sun. Still others came after perihelion, as the object was heading back out. Did the object's appearance change over time? If it was a comet, you'd expect more activity near perihelion. But with observations scattered over weeks and coming from different telescopes under different conditions, it's hard to definitively say whether any changes were real or just artifacts of different observing circumstances. Consider too the challenge of photographing something that's moving fast. 3I/ATLAS wasn't just sitting still in the sky, it was racing through the inner solar system at dozens of kilometers per second. From our perspective on Earth, which is itself moving, the object was changing position noticeably from night to night. Capturing sharp images required precise coordination. Any slight error in tracking, any momentary atmospheric distortion could blur the image. All of this is to say that when astronomers reported seeing or not seeing a coma, they were making honest observations based on complex data. The truth, whatever it is, sits somewhere in those photons, but extracting it requires not just technology but also judgment, experience, and careful statistical analysis. If images were ambiguous, perhaps spectroscopy could provide clearer answers. Spectroscopy is one of the most powerful tools in astronomy. By spreading light into its component wavelengths, you can identify the chemical composition of distant objects. Every atom and molecule has a unique spectral signature, specific wavelengths where it absorbs or emits light. By reading these signatures, you can determine what something is made of, even if it's millions or billions of kilometers away. For comets, spectroscopy is particularly revealing. As ices sublimate and gases stream away from the nucleus, those gases interact with sunlight. They absorb photons at specific wavelengths, and they also fluoresce, re-emitting light at other wavelengths. This creates a complex pattern of bright emission lines and dark absorption lines. By studying this pattern, you can identify exactly which molecules are present and in what quantities. Water is the most common molecule in comets, often making up more than half of the nucleus by mass. When water sublimates, it creates a distinctive signature in the ultraviolet and infrared parts of the spectrum. Carbon monoxide and carbon dioxide are also common, each with their own spectral fingerprints. You can also detect more complex molecules like methane, ammonia, hydrogen cyanide, and various organic compounds. Each comet has a slightly different composition, a chemical personality that reflects where and how it formed. When 3I/ATLAS appeared, several teams immediately attempted spectroscopic observations. This isn't easy. The object was faint, and to get a good spectrum you need to collect a lot of light. This requires large telescopes and long exposure times, but several of the world's best facilities were brought to bear on the problem. The results were frustratingly inconclusive. Some teams reported possible detection of emission lines that might correspond to carbon-bearing molecules, but the signals were weak, barely above the background noise. Other teams, using different instruments or different analysis methods, found no convincing evidence of gas emission. The spectra looked flat, featureless, more like what you'd expect from reflected sunlight off a rocky surface than from an active comet. Why was it so hard to detect gas, assuming it was there? Part of the problem is simply distance and brightness. 3I/ATLAS was never particularly close to Earth during its passage. At its nearest, it was still many millions of kilometres away. The farther an object is, the fainter it appears, and the harder it is to collect enough light for a detailed spectrum. Additionally, if the object was only weakly active, producing gas at a low rate, the spectral signatures would be proportionally weak. There's also the complication of solar contamination. The light we see from a comet is a mix of reflected sunlight and light from the gases. Separating these two components requires careful analysis. If the gas emission is weak and the reflected sunlight is relatively strong, the gas signatures can be swamped and lost in the data. Some researchers tried different wavelength ranges. Ultraviolet observations, which are sensitive to certain molecules, were attempted using space-based telescopes. Infrared observations, which can detect warm dust and different gas species, were also tried. But in each case, the results were at best suggestive, never definitive. The lack of clear gas detection became a key point in the asteroid hypothesis. If you can't see the gas, maybe it's not there. Or maybe it's there in such small amounts that calling the object a comet is misleading. This is where the debate gets into definitions. What makes a comet a comet? Is it the presence of any ice at all? Or does it require active outgassing on a certain scale? These questions, which might seem academic, actually matter when you're trying to understand what you're observing. Let's think about the orbit itself. One of the most powerful ways to study a celestial object is to track how it moves. Gravity is extraordinarily well understood. We can predict with exquisite precision how an object should move under gravitational forces alone. If we see deviations from these predictions, it tells us that something else is at work. When 3I/ATLAS was first detected, astronomers immediately began calculating its orbit. They used Newton's laws of motion and gravity, refined by Einstein's theory of general relativity, to predict where the object should be at any given time. As more observations came in from different locations, the orbit could be refined, becoming more and more precise. But there was a puzzle. Some researchers noticed that the object's position didn't quite match the predictions. The differences were tiny, just a few arcseconds on the sky, which is a minuscule angle. But these differences were systematic, not random. They suggested that something was pushing or pulling on the object in addition to gravity. This is where the non-gravitational acceleration debate comes in. If a comet is releasing gas, that gas carries momentum. As it jets away from the surface, it pushes the nucleus in the opposite direction. This is Newton's third law. Every action has an equal and opposite reaction. For a small comet nucleus, this force can be significant enough to measurably alter its trajectory. The key word here is measurably. The effect is tiny. A comet might experience an acceleration of only millimeters per second squared, far less than the gravitational acceleration from the Sun, which is about 5,000 times stronger at Earth distance. But over weeks and months, this tiny extra push accumulates. The comet ends up in a slightly different place than pure gravity would predict. Several research groups attempted to model this effect for 3I/ATLAS. They took the observed positions and velocities and tried to fit them to a model that included both gravitational and non-gravitational forces. The non-gravitational forces would depend on things like how much gas the comet was producing, in which direction the gas was jetting, and how the comet was rotating. Some of these models suggested that yes, there was a detectable non-gravitational acceleration. The magnitude was small, but it was there. The direction and timing made sense for outgassing near perihelion. This seemed to support the comet hypothesis, but other groups were sceptical. They pointed out that orbital determination is tricky. Small uncertainties in the initial position and velocity can propagate through the calculations. Observations from different telescopes might have small systematic errors. The gravitational influence of planets has to be accounted for precisely. And there are other non-gravitational effects, like radiation pressure from sunlight and the Yarkovsky effect, that can also perturb an orbit. When these skeptical researchers did their own analysis, often with slightly different assumptions or data weighting, they found that the orbit could be explained by gravity alone within the uncertainties. Any apparent non-gravitational acceleration disappeared when you accounted for all the error sources. This is a common situation in science. When you're measuring something at the very edge of detectability, different analysis methods can yield different conclusions. It doesn't mean anyone is doing bad science. It means the signal is genuinely ambiguous. More data would help, but by the time these analyses were being done, 3I/ATLAS was already on its way out of the solar system, growing fainter and fainter until it could no longer be observed. The debate over the orbit highlights a deeper point about interstellar objects. We get one chance to observe them. Unlike asteroids and comets that orbit the Sun and come back periodically, interstellar visitors pass through once and are gone forever. This makes every observation precious and every analysis critical. But it also means we have to accept that some questions might remain unanswered. To better understand 3I/ATLAS, it helps to compare it to other objects. What do we know about interstellar visitors in general? How does 3I/ATLAS fit into the broader picture? Oumuamua, the first confirmed interstellar object, was discovered in October of 2017. It caused a sensation. For the first time, we had proof that objects from other solar systems could pass through ours. Oumuamua was fascinating and frustrating in equal measure. It was shaped oddly, possibly like an elongated cigar or perhaps a flat pancake. It showed no obvious cometary activity, no coma, no tail. Yet it accelerated away from the Sun in a way that suggested something was pushing it. The debates over Oumuamua were fierce. Was it a comet with unusual properties? Was it an asteroid experiencing the Yarkovsky effect? Some researchers even suggested more exotic possibilities, like a light sail built by an alien civilization, though this was always a fringe idea. Most scientists favoured natural explanations, but the data was ambiguous enough that no consensus emerged. Oumuamua remains a mystery to this day. Then came 2I/Borisov in August of 2019. This object was refreshingly straightforward. It had a bright coma, it released gas that could be easily detected, it behaved like a comet in every way. Spectroscopic observations showed water vapour, carbon monoxide, and other typical cometary molecules. Its composition was remarkably similar to comets from our own solar system, suggesting that comet formation might be a universal process. 2I/Borisov was everything Oumuamua wasn't. Conventional, understandable, comforting. Now 3I/ATLAS sits somewhere between these two extremes. It's not as mysterious and ambiguous as Oumuamua, but it's also not as straightforward as 2I/Borisov. It might have had a weak coma, or it might not have. It might have outgassed slightly, or it might not have. It occupies an uncertain middle ground. This raises an interesting question. Are interstellar objects fundamentally different from objects in our solar system, or are they basically the same? If they're the same, then the comets and asteroids wandering between the stars should look and behave like the comets and asteroids we're familiar with. But if planetary systems are diverse, forming under different conditions with different compositions, then interstellar objects might surprise us. They might be made of materials or mixtures we haven't encountered before. They might behave in ways we don't expect. Some researchers have suggested that interstellar space itself might alter these objects. Cosmic rays, high-energy particles that pervade the galaxy, bombard objects over millions of years. This radiation can break down molecules, alter surface chemistry, and create strange compounds that wouldn't form otherwise. An interstellar comet might have a crust of such altered material on its surface, insulating the pristine ice underneath. When it approaches a star, this crust might prevent normal outgassing until it's heated enough to crack and peel away. There's also the question of how long these objects have been travelling. Some might have been ejected from their home systems only a few million years ago. Others could have been wandering the galaxy for billions of years, ancient relics from the early universe. Age might affect appearance and behaviour. An old comet might have lost much of its volatile material to space weathering. A young one might be pristine. All of this context makes 3I/ATLAS both more and less mysterious. More mysterious because we don't yet know enough about interstellar objects to have firm expectations. Less mysterious because ambiguous observations might simply reflect natural diversity rather than anything truly anomalous. There's a certain humility required when studying objects like 3I/ATLAS. We must acknowledge the limits of our knowledge. We're trying to understand something small and distant with instruments that, despite being marvels of technology, have finite capabilities, and we're doing it over a limited time frame, as the object passes through and then leaves forever. Consider what we were able to measure with confidence. We know that 3I/ATLAS came from outside our solar system. Its trajectory is unambiguous on this point. We know approximately how big it is, based on brightness and reasonable assumptions about reflectivity. We know roughly when it passed closest to the Sun. These facts are solid, but we don't know definitively whether it had a coma. We don't know for certain whether it released gas. We don't know if its trajectory was affected by non-gravitational forces. We don't know what it's made of beyond educated guesses. These uncertainties aren't failures. They're honest acknowledgements of observational limits. In science, especially in astronomy, we often work with incomplete information. We build models, make assumptions, test hypotheses. When the data is ambiguous, different researchers might reasonably favour different interpretations. This isn't a problem to be solved. It's a feature of the scientific process. Disagreement drives deeper investigation. Uncertainty motivates better observations in the future. It's worth noting that the classification of 3I/ATLAS as a comet, an asteroid or something else doesn't change the object itself. Out there in space, now many astronomical units away and receding, 3I/ATLAS is what it is. Our labels are for our convenience, our attempts to categorize and understand. Nature doesn't care about our taxonomies. What matters more than the label is what we learn about interstellar objects in general. Each visitor teaches us something. Oumuamua taught us that such objects exist and that they can surprise us. 2I/Borisov taught us that interstellar comets can be chemically similar to our own comets. And 3I/ATLAS teaches us that ambiguity is okay, that not every observation yields a clear answer, and that the universe contains things that don't fit neatly into our boxes. There's also a practical lesson here about the importance of preparedness. When the next interstellar object arrives, and there will be others, we need to be ready. We need better detection systems to find these objects earlier, giving us more time to observe them. We need coordinated observing campaigns to maximize data collection. And we need faster, more powerful instruments that can characterize faint, fast-moving targets. Some astronomers have proposed missions specifically designed to intercept interstellar objects. Imagine a spacecraft on standby, ready to launch on short notice when a new visitor is detected. Such a spacecraft could fly alongside the object, making close-up observations, perhaps even landing on it. This would answer definitively the questions that remote observations leave open. but such missions are expensive and technically challenging. They remain dreams for now, though dreams worth pursuing. In the meantime, we continue watching the sky, searching for the next visitor, and we continue debating objects like 3I/ATLAS, not because we enjoy arguing, but because wrestling with ambiguity is how science advances. Let's think more carefully about why different research teams came to different conclusions about 3I/ATLAS. Part of the answer lies in the tools they used and the methods they employed. Astronomy is not a monolithic enterprise. Different observatories have different capabilities, different researchers have different areas of expertise, and these differences matter. Some teams used optical telescopes, which observe visible light. Others used infrared telescopes, sensitive to heat radiation. Still others attempted observations in the ultraviolet. Each wavelength range reveals different aspects of an object. Visible light shows us reflected sunlight, which tells us about surface properties and albedo. Infrared light can detect warm dust and certain gas molecules. Ultraviolet light is absorbed by various atoms and molecules, creating diagnostic spectral features. The challenge is that 3I/ATLAS was observable from Earth for only a limited time, and during that window not all telescopes were available. Observing time on major facilities is precious, allocated months in advance based on competitive proposals. When a new object is discovered, there's a scramble to get observing time. Some teams were successful, others were not. Moreover, weather and atmospheric conditions play a role. Astronomy is at the mercy of clouds. A team might have precious hours of telescope time booked, only to lose it all to bad weather. Or atmospheric turbulence might blur the images, reducing the quality of data, or the moon might be bright, washing out faint details. All of these factors affect what can be seen and measured. Then there's the matter of data processing. Raw astronomical images aren't like photographs. They're numerical arrays, measurements of a light intensity at each pixel. To extract meaningful information, these arrays must be processed, corrected for instrumental effects, calibrated against standard stars, aligned and stacked if there are multiple exposures. Different researchers use different software and different algorithms for this processing. While the results should be similar, subtle differences can emerge, especially for faint marginal detections. Consider the coma question again. One team might use a particular software package to subtract the background sky and model the point spread function. Their analysis shows that 3I/ATLAS is slightly extended compared to stars. Another team uses a different package with different assumptions. They find no significant extension. Who's right? Possibly both. One set of choices might be slightly more sensitive to real extension. The other might be more conservative, avoiding false positives. Without a ground truth, it's hard to say definitively. The same issues arise with spectroscopy. Extracting a spectrum from a faint object requires careful subtraction of sky background, which itself contains emission lines from Earth's atmosphere and scattered moonlight. Different teams might handle this differently. Some might apply aggressive smoothing to reduce noise, which can enhance weak signals but might also introduce artifacts. Others might prefer minimal smoothing, preserving detail but potentially missing faint features in the noise. All of this is to say that science is done by humans using imperfect tools under less than ideal conditions. The remarkable thing is not that researchers sometimes disagree, but that they agree as often as they do. Through careful cross-checking, replication and peer review, the scientific community converges on truth. But convergence takes time, and for objects like 3I/ATLAS, time is limited. Beyond observations, there's the role of theoretical models. To interpret what we see, we must compare it to what we expect, and expectations come from models, which are simplified representations of complex reality. Models are incredibly useful, but they're only as good as the assumptions that go into them. For example, when estimating the size of 3I/ATLAS from its brightness, astronomers assume a certain albedo. If the albedo is higher than assumed, the object is smaller than calculated. If it's lower, the object is larger. But we don't know the albedo precisely without measuring it directly, which requires resolved imaging that we didn't have. So we guess based on what seems reasonable for comets or asteroids. Similarly, when modelling potential outgassing, researchers must assume things like the composition of ices, the rotation state of the nucleus, the distribution of active areas on the surface, and how sunlight heats the object. These assumptions are informed by studies of comets in our solar system, but an interstellar object might not behave the same way. It might rotate faster or slower. It might have a different thermal inertia. Its ices might sublime at different temperatures. Different teams might make different assumptions, leading to different predictions. One team's model might predict that significant outgassing should be visible if the object is a comet. When they don't see it, they conclude the object is probably not a comet. Another team uses a more conservative model that predicts weaker activity. The lack of strong observed activity fits their expectations, so they remain open to the comet interpretation. There's also the question of prior beliefs. Scientists try to be objective, but everyone brings their own experiences and intuitions to the table. A researcher who has spent years studying comets might be more inclined to see cometary behaviour in ambiguous data. A researcher who specialises in asteroids might lean the other way. These biases aren't necessarily conscious or deliberate. They're part of how we process information. Bayesian reasoning, a formal framework for updating beliefs based on evidence, acknowledges this explicitly. You start with a prior probability, your initial belief about how likely something is. Then you update that probability based on new evidence. But different priors can lead to different conclusions even with the same evidence. If you started out thinking interstellar comets are common, you might need less evidence to classify 3I/ATLAS as one. If you thought they're rare, you might demand stronger proof. The scientific ideal is to let the data speak for itself, to be guided by evidence rather than preconceptions. But in practice, when data is ambiguous, interpretation is unavoidable. The best we can do is be transparent about our assumptions, test them rigorously, and remain open to changing our minds when new evidence arrives. In the case of 3I/ATLAS, both sides of the debate have published their analyses in peer-reviewed journals. They've shown their methods, their assumptions, their reasoning. Other researchers can examine the work, replicate the calculations, and form their own opinions. This is how science self-corrects over time, not through immediate consensus, but through sustained engagement with evidence and ideas. Let's dive deeper into a central question. What does it mean for an object to be active? This might seem straightforward, but it's more nuanced than it appears. Activity in the context of comets typically means the release of gas or dust that creates an observable coma or tail. But how much activity is required? Is a tiny puff of gas enough? Or must there be sustained, vigorous outgassing? In our solar system, we've observed a spectrum of activity levels. Some comets, when they approach the sun, become incredibly active. They develop huge comas millions of kilometres across and tails that can stretch halfway across the sky. These are the spectacular comets that make headlines and become visible to the naked eye. Comet Hale-Bopp, which passed through the inner solar system in 1997, was one such object. Its coma was larger than the Sun, and its tails were visible for months. But most comets aren't like that. The vast majority are faint, with small comas and no obvious tails. They might release water and other gases at rates of only a few kilograms per second, far less than their more famous cousins. Some comets are so weakly active that they're almost indistinguishable from asteroids. These objects, sometimes called transition objects or Manx comets, challenge our definitions. They're also objects that seem to switch on and off. They're inactive for most of their orbit, looking like asteroids, but then become briefly active when they're closest to the Sun, or they might have occasional outbursts, brief periods of intense activity followed by long, quiet stretches. The mechanisms behind these behaviours are still being studied. They might involve ice buried beneath an insulating layer of dust, or pockets of volatile material that suddenly rupture. Given this diversity, how should we think about 3I/ATLAS? If it had any activity at all, even at a very low level, does that make it a comet? Or should we reserve the term comet for objects with clear, unambiguous outgassing? This isn't just semantics. It's about how we organise our understanding of the solar system and beyond. Some researchers advocate for a broad definition. Any object with detectable outgassing, no matter how weak, should be called a comet. This captures the fundamental difference between icy and rocky bodies. Others prefer a narrower definition that requires a certain level of activity. This keeps the term meaningful and prevents us from calling everything a comet based on marginal detections. There's also the practical issue of verification. If activity is barely detectable, how confident can we be that it's real? In astronomy, we typically require a signal to be at least 3 standard deviations above the noise to consider it a detection. This is the famous 3 sigma rule. But even then, with so many observations being made, some detections will be statistical flukes. If you look at enough objects, eventually one will appear to be active by chance alone. For 3I/ATLAS, the alleged activity was right at this threshold. Some measurements suggested 3 to 4 sigma detections of a coma or spectral features. Others found nothing above 2 sigma, which isn't considered convincing. In this regime of marginal detections, honest disagreement is inevitable. It's worth considering that the answer might not be binary. Perhaps 3I/ATLAS is neither a pure comet nor a pure asteroid, but something in between. Perhaps it's a body that was once more active but has since lost most of its volatile material. Or perhaps it's a rubble pile, a mix of icy and rocky components, where the ratio happens to be such that activity is minimal. The universe is under no obligation to fit our categories neatly. Behind all the data and models and analysis are people. Scientists are human, with all the complexities that entails. Understanding scientific debates requires acknowledging this human element. It's not just about evidence, it's also about communication, collaboration, competition, and sometimes ego. When 3I/ATLAS was discovered, multiple research groups raced to observe it and publish their findings. In astronomy, as in many fields, there's pressure to be first. The first team to report a discovery or make a significant finding gets the credit, the citations, the recognition. This can be a powerful motivator. It drives researchers to work quickly, to analyse data efficiently, to write papers rapidly. But speed can come at the cost of thoroughness. There's a tension between getting results out fast and checking everything meticulously. Most researchers try to balance these competing demands, but mistakes happen. A preliminary analysis might suggest something exciting, only to be revised when more data comes in. An initial claim might be walked back when other teams can't replicate the result. In the case of 3I/ATLAS, some early reports were optimistic about the detection of a coma and gas emission. These reports generated excitement and press coverage. But as more observations accumulated and more thorough analyses were done, the picture became less clear. Some researchers who had initially been confident about the comet classification became more cautious. Others doubled down, arguing that their original interpretation was correct. This evolution is normal and healthy. Science is self-correcting. But it can be confusing to outsiders. Why can't scientists just agree? Why do they keep changing their minds? The answer is that science is a process, not a fixed body of facts. Our understanding evolves as evidence accumulates. There's also the matter of communication between research groups. Ideally, scientists would share data and analyses freely, working together to get the right answer. In practice, there can be territoriality. A group that has invested time and resources in observing an object might be reluctant to share their data before they've published their own paper. This is understandable, but it can slow down progress and lead to duplication of effort. Professional astronomy has mechanisms to encourage collaboration. Observatories often have data-sharing policies. Journals require that data be made available upon publication. International organisations coordinate observing campaigns for special events. But these mechanisms aren't perfect, and competition can still create friction. Personalities matter too. Some researchers are cautious and conservative, reluctant to make strong claims without overwhelming evidence. Others are more bold, willing to advocate for an interpretation based on suggestive but not conclusive data. Neither approach is wrong. Science needs both types of people. The cautious ones keep us honest, preventing premature conclusions. The bold ones push boundaries, proposing new ideas that might turn out to be correct. The debate over 3I/ATLAS involves respected researchers on both sides. These are people who have spent their careers studying comets, asteroids, and interstellar objects. They know the field deeply. Their disagreement isn't because anyone is incompetent or dishonest. It's because the evidence genuinely allows for multiple interpretations. Recognizing this helps us appreciate the debate not as a failure, but as science working as it should. Looking back at the history of astronomy, we find many cases where initial classifications were uncertain and debates raged for years or even decades. These historical examples can provide perspective on the 3I/ATLAS controversy. Consider Pluto. When Clyde Tombaugh discovered it in 1930, it was immediately classified as the 9th planet. For decades, this classification went unchallenged. But as our understanding of the outer solar system improved, and as more objects similar to Pluto were discovered, doubts arose. Was Pluto really a planet, or was it something else? The debate culminated in 2006. When the International Astronomical Union officially reclassified Pluto as a quote 4, this decision was controversial and remains a topic of passionate discussion even now. The point isn't whether the reclassification was right or wrong. The point is that categories in science are human constructs, and they can change as our knowledge grows. Pluto didn't change. Our understanding of what it means to be a planet changed. Similarly, 3I/ATLAS is what it is, regardless of whether we call it a comet or an asteroid. Another example, the asteroid Ceres. Discovered in 1801, it was initially classified as a planet. Later, as more asteroids were found, it was reclassified as an asteroid. Then, in 2006, along with Pluto, it was designated a dwarf planet. So Ceres has been a planet, an asteroid, and a dwarf planet over the course of 2 centuries, even though the object itself hasn't changed. What changed was our framework for classification. There's also the fascinating case of Chiron, discovered in 1977. It orbits between Saturn and Uranus, and was initially classified as an asteroid. But in 1988, astronomers noticed it had developed a coma. It was outgassing like a comet, so it was reclassified as a comet, or more precisely as both a comet and an asteroid, given the dual designation 2060 Chiron and 95P/Chiron. Chiron belongs to a class of objects now called centaurs, which are icy bodies in the outer solar system that have characteristics of both asteroids and comets. The discovery of Chiron and other centaurs forced astronomers to expand their taxonomy and recognise that nature doesn't always fit into neat boxes. These historical examples teach us several lessons. First, classification schemes are tools for organising knowledge, not fundamental truths. Second, ambiguity and reclassification are normal parts of the scientific process. Third, when new types of objects are discovered, it takes time to figure out where they fit. Interstellar objects are new to us. Oumuamua was only discovered in 2017. We've only confirmed 3 such objects so far. We're still learning what they look like, how they behave, what they're made of. It would be strange if we had it all figured out already. The debates and uncertainties surrounding 3I/ATLAS are signs that we're grappling with something genuinely new, expanding our knowledge into previously unexplored territory. In 100 years, with perhaps hundreds of interstellar object observations, we'll likely have a much clearer picture. We'll know the typical properties, the range of compositions, the activity levels. We'll have better classification schemes. And perhaps we'll look back at the 3I/ATLAS debate with the same amused perspective that we now have about arguments over whether Pluto is a planet. But for now, we're in the thick of discovery, and uncertainty is part of the journey. Let's step back from the specifics of 3I/ATLAS and think about the bigger picture. Why do interstellar objects matter? What can they teach us that we can't learn from objects in our own solar system? The answer is that interstellar objects are messengers. They carry information about other planetary systems, other stars, other environments. Every star system forms through the collapse of a cloud of gas and dust. In the resulting disk of material, planets and smaller bodies coalesce. The composition of these bodies reflects the composition of the original cloud, which in turn depends on the history of the galaxy in that region. Stars form in different parts of the galaxy at different times with different metallicities. Metallicity, in astronomical terms, means the abundance of elements heavier than hydrogen and helium. The first stars in the universe had almost no metals because the Big Bang produced only hydrogen, helium, and traces of lithium. Heavier elements were forged in the cores of stars and spread through space when those stars exploded. Each generation of stars has slightly more metals than the last, as the galaxy chemically enriches over time. A planetary system that formed early in the galaxy's history might have very different composition than one that formed recently. Similarly, systems that formed in the dense stellar nurseries near the galactic centre might differ from those in the sparse outer regions. By studying objects from different systems, we can probe this diversity. But there's a problem. Most planetary systems are far away, hundreds or thousands of light years. We can detect planets around other stars using indirect methods, like watching for the slight wobble they cause in their star's motion, or the tiny dimming when they pass in front of the star. We can even, in some cases, image giant planets directly. But small bodies like comets and asteroids are far too small and faint to see at interstellar distances. That's where interstellar objects come in. Occasionally a comet or asteroid gets ejected from its home system through gravitational interactions. These rogue objects then wander through the galaxy. Most will never encounter another star, but a tiny fraction by chance will pass through another planetary system. And if we're watching carefully, we can spot them. Each interstellar object is a free sample from another planetary system. We don't know which system, and we likely never will. But we can study the object itself, determine its composition, measure its properties, and compare it to objects in our own system. Over time, as we observe more and more interstellar visitors, we'll build up a statistical picture of what's out there. Are interstellar comets chemically similar to our comets, suggesting that comet formation is a universal process? Or are there significant differences, hinting at diverse formation environments? Are interstellar asteroids common? How about more exotic objects, like icy bodies that never experience the heat of star formation, or fragments from collisions that destroyed planets? Every interstellar object, even one as ambiguous as 3I/ATLAS, contributes to this picture. The uncertainty about whether it's a comet or asteroid might itself be informative. Perhaps interstellar space is populated by many transition objects, bodies that don't fit neatly into categories. This would tell us something about how planetary systems evolve and what types of objects get ejected. How do objects end up in interstellar space? Understanding the ejection process is key to interpreting what we see in interstellar objects. It's a story of planetary dynamics played out over millions of years. When a planetary system forms, the protoplanetary disk contains countless small bodies. Most of this material eventually accretes onto planets or falls into the star, but some remains, forming asteroid belts and comet reservoirs. In our solar system, the asteroid belt lies between Mars and Jupiter. The Kuiper belt beyond Neptune contains icy bodies, including Pluto. And far beyond that, the Oort cloud is a spherical shell of trillions of comets extending halfway to the nearest star. These reservoirs are not stable forever. Gravitational perturbations from planets can change the orbits of small bodies. Most of the time, these changes are small, nudging an object into a slightly different orbit. But occasionally a series of close encounters can drastically alter a trajectory. An object might be sent inward toward the Sun, where it could become a periodic comet, or it might be flung outward, gaining so much speed that it escapes the system entirely. The most efficient ejectors are massive planets. In our solar system, Jupiter is the dominant player. Its enormous gravity can slingshot objects to escape velocity. In fact, simulations suggest that for every object Jupiter sends into the Sun, dozens are flung out of the solar system, over billions of years. Jupiter and the other giant planets have ejected countless comets and asteroids. Other planetary systems likely work the same way, though the details vary. A system with multiple giant planets might be especially efficient at ejection. A system where a planet migrated inward, moving closer to its star over time, would have scattered many small bodies. And in binary or multiple star systems, the gravitational dynamics are even more complex, potentially leading to even more ejections. What happens to an ejected object? It becomes a wanderer, moving through the galaxy under the influence of the galaxy's overall gravitational field. It's no longer bound to any star. Over time, it will move through various environments, dense molecular clouds, open space between stars, perhaps even close to other stars. Each environment subjects it to different conditions. In interstellar space, far from any star, temperatures plunge close to absolute zero, just a few degrees above the cosmic microwave background. At these temperatures, any remaining volatile materials are locked in solid form. The object is essentially frozen in time, preserved in a state similar to when it was ejected. But it's not entirely isolated. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, constantly bombard it. Over millions of years, this radiation can alter surface chemistry, breaking down complex molecules and creating new compounds. Interstellar gas, though extremely tenuous, can slowly erode surfaces. And occasionally the object might pass through a denser region, like a molecular cloud, where interactions with gas and dust are more significant. When such an object eventually encounters another planetary system like ours, it's carrying a record of all these experiences. Its surface might be radiation damaged. Its orbit might have been slightly bent by previous stellar encounters. Its interior, however, might still be pristine, unchanged since it formed billions of years ago. Understanding this history helps us interpret objects like 3I/ATLAS. If it's a comet with weak activity, perhaps it's because the surface is coated with an insulating layer of radiation-processed material. The ice is still there, deep down, but it's not easily released. If it's an asteroid, perhaps it was originally an icy body that lost its volatiles through some process during its long journey. How common are interstellar objects? This is one of the most important questions in the field. If they're rare, our chances of studying many examples are limited. If they're common, we might observe dozens or hundreds in the coming decades. The answer has implications for how planetary systems form and evolve. Based on the few detections we have so far, astronomers have tried to estimate the density of interstellar objects in our local region of the galaxy. The calculation is tricky. You need to know the volume of space you're effectively surveying, the sensitivity of your detection methods, and how long you've been looking. Small objects or dark objects will be missed. Fast-moving objects might pass through before they're detected. All these factors must be accounted for. The estimates suggest that within a sphere of radius, 1 astronomical unit, roughly the distance from the Earth to the Sun, There is typically at least one interstellar object larger than 100 meters across at any given time. That might sound like a lot, but space is vast. The volume of a sphere 1 astronomical unit in radius is enormous, and a 100-meter object within it would be nearly impossible to find unless it happened to pass very close to Earth. To put this in perspective, imagine shrinking the solar system so that the Sun is the size of a basketball. On this scale, Earth would be a tiny pea about 25 meters away. Jupiter would be the size of a large marble 130 meters away. And the nearest star would be over 6,000 kilometers away. Now imagine trying to spot a grain of sand somewhere in that vast empty space between the basketball sun and the nearest star. That's the challenge of finding interstellar objects. The fact that we've detected 3 so far is actually impressive. It's a testament to improved survey technology and diligent sky monitoring. Surveys like Atlas, Pan-STARRS and others scan the sky every night, automatically flagging anything that moves. Software algorithms filter through millions of detections, looking for the unusual ones. Human astronomers then follow up on the most promising candidates. As these surveys improve, becoming more sensitive and covering more of the sky more frequently, the detection rate should increase. Some estimates suggest we might find 1 or 2 interstellar objects per year in the near future. Within a decade, we could have dozens of examples. This would transform the field from studying individual curiosities to performing population statistics. We could ask questions like, what's the ratio of icy to rocky interstellar objects? Do they come preferentially from certain directions, perhaps indicating nearby regions of recent star formation? Are there correlations between size and composition? Each new detection adds a data point, and with enough data points, patterns emerge. There's also the question of much smaller objects. The estimates mentioned above are for objects at least tens or hundreds of meters across. But there are surely many more smaller objects, perhaps down to pebble-sized or even dust-sized. These are impossible to detect individually, but they could be detected collectively if enough of them impact spacecraft or Earth's atmosphere. In fact, some researchers have proposed that certain unusual meteors might be of interstellar origin, though proving this is difficult. The density of interstellar objects also tells us about the efficiency of planet formation and the typical dynamics of planetary systems. If interstellar space is full of ejected material, it suggests that planetary systems are messy, chaotic places, at least during their early histories. If interstellar objects are rare, it might mean that most planetary systems are stable, with little ejection. The data we're gathering now will eventually answer these questions. What does the future hold for the study of interstellar objects? There are reasons for optimism. Technology is improving, new telescopes are coming online, and there's growing recognition that these objects are worth studying intensively. One of the most anticipated astronomical facilities is the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope or LSST. Located in Chile, this observatory will begin full operations in the mid-2020s. It will survey the entire visible sky every few nights, detecting anything that changes or moves. It's expected to revolutionize many areas of astronomy, including the detection of asteroids, comets, and interstellar objects. Simulations suggest that the Rubin Observatory could detect 1 to 10 interstellar objects per year, depending on their actual density in space and their size distribution. That would mean dozens of interstellar visitors catalogued over the observatory's planned 10-year survey. Each would be tracked, measured, and studied. We'd finally have a statistically significant sample. Beyond detection, there's the dream of rendezvous missions. The European Space Agency's Comet interceptor mission, planned for launch in the late 2020s, is designed to do exactly this. It will wait in space at the Sun-Earth Lagrange point, a gravitationally stable location. When a suitable target is identified, whether a new comet from the Oort cloud or an interstellar object, the spacecraft will quickly adjust its trajectory to intercept. Such a mission could answer definitively the questions that observations from Earth cannot. It could measure composition directly by analysing dust particles, It could image the nucleus at high resolution, revealing surface features. It could fly through the coma, measuring gas composition in situ. For an object like 3I/ATLAS, a rendezvous mission would immediately resolve whether it's a comet, an asteroid, or something else. There are also proposals for more ambitious missions. Imagine a spacecraft specifically designed to chase down interstellar objects, equipped with propulsion systems that could match the object's high velocity. Such a spacecraft could accompany the object for extended periods, studying it in detail as it passes through the solar system. These concepts are still in the early stages, facing technical and financial challenges, but they're not beyond the realm of possibility. On the ground, next-generation telescopes like the extremely large telescope in Chile and the Giant Magellan Telescope will offer unprecedented light-collecting power and resolution. They could characterize interstellar objects in much greater detail, perhaps even detecting individual molecules in their atmospheres if those objects are active enough. There's also the potential for international collaboration. When an interstellar object is detected, it triggers a global response. Astronomers from many countries contribute observations. Data is shared, often in real time. This kind of collaboration is science at its best, transcending borders and rivalries in pursuit of knowledge. The study of interstellar objects is still in its infancy. We're like naturalists in the age of exploration, encountering strange new creatures and trying to figure out where they fit in the tree of life. The debates and uncertainties are part of the excitement. Each new detection brings surprises and challenges, and as our capabilities grow, so too will our understanding. Let's take a moment to reflect on a deeper question. Why do we classify things? What purpose does it serve, and what are the limits of classification? Humans are pattern seekers. We instinctively organize the world into categories. This is evident in language itself. We have words for quote 5, quote 6, quote 7, even though each tree, each rock, each cloud is unique. The categories are abstractions, mental shortcuts that allow us to communicate and reason efficiently. In science, classification serves several purposes. It helps us organize knowledge. Imagine trying to study biology without the concept of species, or chemistry without the periodic table. Classification provides structure, a framework for understanding relationships and patterns. It also facilitates communication. When astronomers say, quote 8, they're conveying a lot of information in a compact way. You immediately know it's an icy body, that it likely formed in the outer solar system, that it might become active when heated. But classification has limits. Nature is messier than our categories. There are always edge cases, objects that don't fit neatly into boxes, and sometimes our categories reflect more about our history and biases than about fundamental natural divisions. Consider the comet-asteroid distinction. Historically, it was based on appearance. Fuzzy object with a tail equals comet. Sharp point of light equals asteroid. This worked well for a long time. But as we studied these objects more closely, we realized that appearance isn't always a reliable guide to composition or origin. Some asteroids are icy. Some comets are mostly rock. The boundary is blurry. Modern classification tries to be based on intrinsic properties rather than appearance. Comets are defined as objects with significant volatile content that can outgaze. Asteroids are primarily rocky or metallic, but even this isn't perfect. How much volatile content is significant? What counts as outgassing? These definitions require judgment calls. In the case of 3I/ATLAS, the debate over its classification reflects these underlying ambiguities. It's not that one side is right and the other wrong. It's that the object exists in a grey zone where different reasonable definitions lead to different conclusions. This is frustrating if you want clear, definitive answers. But it's also philosophically interesting. There's a branch of philosophy called metaphysics that deals with questions about the nature of reality and existence. One topic in metaphysics is the problem of universals. Do categories exist independently of our minds, or are they human constructs? If all humans disappeared tomorrow, would there still be a distinction between comets and asteroids? One view, called realism, says yes. Categories reflect real divisions in nature. Another view, called nominalism, says no, categories are just convenient labels we've invented. Most scientists are practical about this. They don't worry too much about deep metaphysical questions. They use categories as tools, refining them when needed, and don't get too attached to any particular scheme. But occasionally, cases like 3I/ATLAS force us to confront the limitations of our categories and to think about what we're really doing when we classify. Perhaps the lesson is humility. Our classifications are provisional, subject to revision. They're not ultimate truths, but useful fictions. When we say quote 10 or quote 11, we're not making a metaphysical claim about the essence of the object. We're saying that based on certain criteria, it's useful to group this object with others that share similar properties. If the criteria change, or if we learn something new, we can reclassify without having been wrong before. We've spent a long time exploring the details of 3I/ATLAS and the debates surrounding it. Now, as we move into the final part of our journey, let's think about what this all means, not just for astronomy, but for how we understand knowledge and uncertainty. In popular culture, science is often portrayed as a source of definitive answers. Scientists are supposed to know things. They study the world, gather data, and deliver conclusions. When scientists disagree or express uncertainty, it can be perceived as a failure or a sign that something is wrong. But this perception misunderstands what science actually is. Science is not a collection of facts. It's a method for understanding the world. The method involves observation, hypothesis, testing, and revision. Uncertainty is built into the process. In fact, uncertainty is essential. It's what drives science forward. If we were certain of everything, there would be nothing left to discover. The debate over 3I/ATLAS is a perfect example. We have limited data, multiple possible interpretations, and honest disagreement among experts. But this isn't a crisis. It's science working as intended. Researchers are carefully examining evidence, considering alternatives, testing ideas. Over time, as more interstellar objects are studied, a clearer picture will emerge. The uncertainty of today feeds the knowledge of tomorrow. There's also a deeper point about the nature of reality. The universe doesn't come pre-labelled. There's no cosmic ledger that says, quote, 13 or, quote, 14. These are human categories, tools we've created to make sense of a complex universe. The object itself is just an arrangement of atoms and molecules in space, following physical laws. Whether we call it a comet or an asteroid doesn't change what it is. This might sound like relativism, the idea that truth is subjective, but it's not. There are objective facts about 3I/ATLAS, its trajectory, its size, its composition. These facts exist independently of our observations or opinions, but the categories we use to describe those facts are human constructs. And like all constructs, they're imperfect and subject to revision. Learning to live with uncertainty is a valuable skill, not just in science, but in life. We want clear answers. We crave certainty. But the world is often ambiguous. Situations are complex, information is incomplete, and multiple perspectives are valid. The ability to hold multiple possibilities in mind without prematurely collapsing to a single conclusion is a form of wisdom. In science, this is formalized through concepts like confidence intervals and Bayesian probabilities. Instead of saying quote 15, we say quote 16. This honest acknowledgement of uncertainty is more valuable than false certainty. So when experts debate whether 3I/ATLAS is a comet or an asteroid, they're not failing. They're demonstrating the rigor and honesty that makes science trustworthy. They're showing us that knowledge is a process, not a finished product. And they're reminding us that the universe is rich and complex, full of subtleties that resist easy categorization. There's something profoundly beautiful about interstellar objects. They're gifts from the cosmos, messengers bearing stories from distant places and times. Each one that passes through our solar system is a connection to the wider galaxy, a reminder that we are part of something much larger. Think about the journey of 3I/ATLAS. It formed around another star billions of years ago, perhaps at the same time Earth was forming. It condensed from the swirling disk of gas and dust that surrounded that young star. For eons it orbited in the outer reaches of its home system, cold and dark and alone. Then, through some gravitational accident, it was flung outward, leaving the only sun it had ever known. For hundreds of thousands of years, or perhaps millions, it drifted through the galaxy. It passed through regions where stars are being born, vast clouds of gas lit by the ultraviolet radiation of massive young stars. It passed through the emptiness between spiral arms, where space is darker and quieter. It may have passed within a few light years of other stars, feeling the faint tug of their gravity, not enough to capture it, but enough to slightly alter its path. And then, by pure chance, its trajectory brought it toward our sun. It fell inward, accelerating as the sun's gravity pulled it. It swept past the orbits of Jupiter, Mars, Earth. For a few weeks in late 2020, astronomers on our planet noticed it, photographed it, wondered about it, and then it passed on, heading back out into the dark, never to return. In a few thousand years, 3I/ATLAS will be far beyond the Kuiper Belt, beyond even the Oort cloud. In 10,000 years, it will be light years away, between stars again. In 1,000,000 years, it might pass through another planetary system, and if that system has astronomers, they too will wonder what it is and where it came from. This perspective, this sense of deep time and vast space, is one of the gifts astronomy offers. It reminds us that our individual lives, even our entire civilization, are brief moments in a much longer story. The stars and the objects between them have been here far longer than we have, and they will continue long after we're gone. But while we're here, we can look up. We can study these visitors. We can try to understand them. And in doing so, we connect with the cosmos in a meaningful way. We're not separate from the universe, looking at it from outside. We're part of it, made of the same elements, governed by the same laws. When we study an interstellar object like 3I/ATLAS, we're studying family, distant cousins from another branch of the cosmic tree. There's also a humbling aspect to this. The universe doesn't care about our debates or our classifications. It doesn't care whether we call something a comet or an asteroid. It doesn't care if we understand or not. The universe simply is, unfolding according to physical law, indifferent to our struggles to comprehend it. And yet, we try. We build telescopes. We develop theories. We debate evidence. We write papers and give talks and teach students. We do all this because understanding matters to us. It's part of what makes us human. We are the part of the universe that has become conscious of itself, that looks back and asks, quote, 17, quote, every interstellar object is a new piece of the puzzle. Every observation, every spectrum, every orbital calculation adds to our knowledge. Even the ambiguous ones like 3I/ATLAS teach us something. They teach us about the limits of our methods, the complexity of nature, and the importance of humility. These are not small lessons. Let's sit with the uncertainty for a moment. Let's appreciate the fact that we might never know for certain whether 3I/ATLAS was a comet or an asteroid, and let's consider that this might be okay. In our daily lives, we're surrounded by questions without definitive answers. What is the meaning of life? What happens after we die? Is there other intelligent life in the universe? These are profound questions, ones that humans have grappled with for millennia. Different people have different answers, informed by philosophy, religion, science, or personal experience, and that's okay. The questions themselves have value, even if the answers remain elusive. In science, we prefer to focus on questions that can, in principle, be answered. We design experiments, make predictions, test hypotheses. This approach has been incredibly successful. But not every scientific question has a clear answer, at least not with current technology and knowledge. And that's okay too. There's a phrase in physics, shut up and calculate. It's a somewhat tongue-in-cheek response to deep philosophical questions about quantum mechanics. Quantum mechanics works. It makes predictions that are confirmed by experiments to extraordinary precision. But what it? Quote, Justine. What the mathematics says about the fundamental nature of reality is still debated. Different interpretations exist, and we don't have a way to definitively choose between them. So some physicists say, shut up and calculate. Focus on what the theory predicts, not on what it means. But many physicists don't shut up. They continue to grapple with the meaning, the interpretation, the philosophy. And this is valuable. Even if we can't settle the question now, the debate sharpens our thinking, reveals new questions, and sometimes leads to unexpected insights. The same is true for questions like the nature of 3I/A TLAS. We might not resolve it. But the attempt to resolve it has taught us a great deal. We've learned about the challenges of observing faint distant objects. We've learned about the subtleties of cometary activity. We've learned about the diversity of small bodies in the solar system and beyond. And we've learned about how science works, how experts can disagree while still respecting each other and the evidence. There's also something aesthetically pleasing about a good mystery. Stories need tension, and questions provide that tension. A universe where everything is known and settled would be boring. The fact that there are still mysteries to solve, still phenomena that puzzle us, makes science exciting. Each unanswered question is an invitation to discovery. Consider some of the great mysteries in astronomy. Dark matter. We know it exists because of its gravitational effects. But we don't know what it's made of. Dark energy. It's accelerating the expansion of the universe, but we don't know what it is. The origin of life. We know it happened on Earth, and we have theories, but we don't know the exact mechanisms. These mysteries drive research, motivate careers, and capture public imagination. 3. I/ATLAS is a small mystery by comparison, but it's part of the same tapestry. The universe is full of puzzles, and we're slowly piecing them together. Each solved puzzle reveals new questions. It's an endless process, and that's part of the joy. So when we ask, what is 3I/ATLAS? And the answer is, we're not sure, we can appreciate that uncertainty. We can sit with it, ponder it, and recognize it as a natural part of the scientific journey. Not every question needs an immediate answer. Some questions are worth living with, letting them shape our thinking, allowing them to lead us to deeper understanding over time. As we near the end of our exploration, let's zoom out one more time. Let's place 3I/ATLAS, and indeed all interstellar objects, in the largest possible context, the story of the universe itself. The universe began 13.8 billion years ago in an event we call the Big Bang. In the first moments, there was only energy, incredibly hot and dense. The temperature was trillions of degrees, far hotter than the core of any star. In this primordial furnace, the laws of physics as we know them were just beginning to take shape. Time and space themselves came into being. Before this moment, there was no before. The very concept of time begins with the Big Bang. As the universe expanded and cooled, particles formed, quarks, electrons, photons. These weren't the stable particles we're familiar with today. They existed in a chaotic dance, constantly being created and destroyed in the intense energy. Within minutes, as the temperature dropped to merely billions of degrees, protons and neutrons combined to form the first atomic nuclei, hydrogen and helium, with traces of lithium and beryllium. This process, called Big Bang nucleosynthesis, lasted only about 20 minutes. But in that brief window, the fundamental composition of the universe was established. roughly 3/4 hydrogen, 1/4 helium. This ratio persists to this day. The universe was still far too hot for atoms to exist. Electrons remained free, not bound to nuclei. The universe was opaque, a hot soup of plasma where light couldn't travel more than a tiny distance before being scattered by free electrons. It was like trying to see through a thick fog, except the fog was the entire universe. After about 380,000 years, the universe cooled enough for atoms to form. This event, called recombination, was a turning point. Electrons combined with nuclei for the first time, creating stable atoms. Suddenly, the universe became transparent. Light could travel freely through space. This is the light we now see as the cosmic microwave background, the afterglow of the Big Bang visible in all directions. When astronomers measure this light today, they're looking back to when the universe was only 380,000 years old, seeing it as it was more than 13 billion years ago. But the universe was still a dark place. There were no stars yet, no galaxies, no structure. Just a nearly uniform gas of hydrogen and helium, slowly expanding and cooling. This period, called the Cosmic Dark Ages, lasted for perhaps 100 million years. During this time, gravity was working quietly, pulling matter together in regions where the density was slightly higher than average. These overdense regions grew. Matter flowed into them, making them denser still. Eventually, the first pockets of gas became dense enough and hot enough that nuclear fusion ignited. The first stars were born. These earlier stars were different from the Sun. They were massive, perhaps 100 times the mass of the Sun or more. They contained almost no elements heavier than helium, because those elements didn't exist yet. They burned fiercely and died young, living only a few million years before exploding as supernovae. And those explosions were crucial. Inside the cores of those first stars, in the intense heat and pressure, hydrogen and helium were fused into heavier elements: carbon, nitrogen, oxygen, silicon, iron. When the stars exploded, these newly forged elements were scattered into space. Mixing with the primordial hydrogen and helium, the universe was being chemically enriched. Subsequent generations of stars formed from gas that contained these heavy elements. These stars could be smaller, longer lived. Around some of them, planets formed. This couldn't have happened around the first stars because planets require heavy elements. You need silicon and iron for rocky planets. You need carbon and oxygen for organic chemistry. You need all the elements that were made in stars and scattered by supernovae. Our Sun is one such later generation star, born about 4.6 billion years ago from a cloud of gas and dust that already contained carbon, silicon, iron, and all the other elements we find on Earth. The Sun itself is about 70% hydrogen, 28% helium, and 2% everything else. That 2% seems small, but it includes all 90 or so naturally occurring elements heavier than helium. All the carbon in our bodies, all the oxygen we breathe, all the iron in our blood, all the calcium in our bones. These were made in stars that lived and died before the Sun was born. In the disk of material around the young Sun, countless small bodies formed. Dust grains stuck together, forming pebbles. Pebbles collided and merged, forming boulders. Boulders accreted into planetesimals, objects kilometers across. Most of these merged to create the planets we know: rocky Mercury, Venus, Earth, and Mars in the inner system, giant Jupiter, Saturn, Uranus, and Neptune in the outer reaches. But not all the planetesimals were incorporated. Some remained, becoming the asteroids and comets we observe today. They're the leftover building blocks, the pieces that never quite made it into planets. And over time, as we've discussed, many of these small bodies were ejected from the solar system. Gravitational interactions with the giant planets, especially Jupiter, flung them outward at high speeds. Some fell into the Sun, others had their orbits changed but remained bound to the solar system. But many achieved escape velocity, leaving the sun's gravitational influence entirely. They became interstellar wanderers, adrift in the galaxy. The same process happened around countless other stars throughout the galaxy. Stars formed from enriched gas clouds. Planets coalesced in the surrounding disks. Small bodies formed and were ejected. This has been happening for billions of years, across billions of star systems. The galaxy, over this vast span of time, became populated with these rogue objects. Some were ejected early, from the first generations of planetary systems that formed when the galaxy was young. Others were ejected more recently, perhaps only a few million years ago. They form a background population, mostly invisible, drifting through the space between stars. The density is low, the galaxy is vast, and even though there are probably trillions of these objects, they're spread out over an enormous volume. Most will never encounter another star. They'll drift for billions of years, perhaps until the galaxy itself changes beyond recognition, until stars cease to form and the universe grows cold and dark in the distant future. But occasionally, by pure chance, one of these wanderers passes close to a star. If that star has planets, and if those planets have developed life, and if that life has evolved intelligence and built telescopes, the object might be detected. This is what happened with 3I/ATLAS. 3I/ATLAS is one such wanderer. Its atoms were forged in stars that exploded billions of years ago, perhaps when the galaxy was half its current age. Those atoms condensed in a protoplanetary disk around a star we'll probably never identify. It could be a star in our neighbourhood, just a few tens of light years away, or it could be a star on the opposite side of the galaxy, thousands of light years distant. We have no way of knowing. The object's current trajectory traced backward doesn't point to any particular star system. It's been travelling too long, its path bent by the gravitational influence of the galaxy itself. It formed in that unknown planetary system, perhaps 4 billion years ago, perhaps 5, perhaps more. It orbited in the cold outer reaches, much as Kuiper belt objects orbit beyond Neptune in our system. Then something happened. Perhaps a giant planet migrated inward, stirring up the small bodies. Perhaps 2 planets had a close encounter, disrupting the entire system. Perhaps the star had a companion star, and the binary dynamics led to chaos. Whatever the cause, 3I/ATLAS was ejected. It travelled for eons, hundreds of thousands of years at least, possibly millions. It passed through the vast emptiness between stars. It may have passed near other stars, feeling their gravity briefly, having its trajectory slightly altered. It experienced the cold of interstellar space. Just a few degrees above absolute zero. It was bombarded by cosmic rays, high-energy particles that slowly altered its surface chemistry. It was alone, utterly alone, for longer than modern humans have existed. And then, its trajectory brought it toward our sun, purely by chance. There was no purpose, no intention, just the mathematics of gravity and motion, playing out over vast scales. It fell inward, accelerating as the sun's gravity pulled it. It swept past the orbits of the outer planets, Neptune, Uranus, Saturn, Jupiter. It passed through the asteroid belt. It reached perihelion, its closest approach to the sun, in early 2021. For a few weeks, it was close enough and bright enough that our telescopes could study it. Astronomers on our planet noticed it, photographed it, debated what it was, and then it passed on, heading back out into the dark, never to return. By now it's already beyond the orbit of Jupiter, moving outward at 34 kilometers per second relative to the Sun. In a few years, it will be beyond Neptune. In a few thousand years, it will be beyond the Oort cloud, that distant shell of comets that marks the edge of the Sun's gravitational dominion. In 10,000 years, it will be light years away, between stars again, back in the interstellar medium where it spent most of its existence. In 100,000 years, it might pass within a few light years of another star. In 1,000,000 years, it might pass through another planetary system. If that system has astronomers, they too will see a faint object passing through. They too will wonder what it is and where it came from. They too will debate its nature, make measurements, write papers. They won't know it came through our solar system. They won't know we saw it too. Our two civilizations, if theirs exists, will be connected only by this silent messenger that visited us both. This perspective makes the debates about its classification seem almost quaint. Whether it's a comet or an asteroid is a human concern, a product of our need to organise and categorise. From the universe's perspective, it's just an arrangement of atoms in motion, one of trillions of similar objects, each with its own story. It doesn't care about our labels. It doesn't know we exist. It simply moves, following the path that gravity and momentum dictate. And yet, those debates matter, because we're part of the universe too. Our questions, our curiosity, our desire to understand, these are as real and as meaningful as anything else in the cosmos. The fact that a small group of astronomers on a small planet circling an average star spent time and effort trying to understand 3I/ATLAS is remarkable. It's a testament to what conscious beings can do. We're not just objects moved by forces. We're observers, thinkers, wanderers. We're made of star stuff, as Carl Sagan famously said. The atoms in our bodies were forged in stellar furnaces, just like the atoms in 3I/ATLAS. We're not separate from the cosmos. We're the cosmos contemplating itself. And when we study an interstellar object, we're engaging in an act of profound connection. We're reaching out across space and time, trying to understand our place in the vast web of existence. We're part of the same story, the same unfolding narrative that began 13.8 billion years ago and continues now, in this moment, as you listen to these words. In this final chapter before we close, let's return to where we started, the idea of peaceful contemplation. Throughout this long journey together, we've explored data, debates, theories, and implications. We've looked at images and spectra, considered orbits and compositions, weighed evidence and arguments. But underlying all of it, threading through every chapter, is a sense of wonder. A sense that the universe is strange and beautiful and full of mysteries worth pondering, even when, perhaps especially when, we cannot fully solve them. Wonder is a fundamental human emotion. It's the feeling we get when confronted with something vast or complex or beautiful that we don't fully understand. It's that catch in your breath when you see a spectacular sunset, that quiet awe when you hold a newborn baby, that sense of vertigo when you truly grasp the scale of the cosmos. Wonder is the mind's response to encountering something that exceeds its grasp, something that reminds us how much there is beyond our everyday experience. Children feel wonder naturally and easily. Everything is new to them. A butterfly is a marvel. A thunderstorm is a spectacle. The stars are jewels scattered across a mysterious dark cloth. They ask why, incessantly, not because they expect complete answers, but because they're genuinely curious. They haven't yet learned to take things for granted. They haven't yet developed the casual indifference that can come with age. As we grow older, we risk losing that sense of wonder. We become familiar with things. We learn names and categories. We develop routines and habits. The world becomes known, mapped, domesticated. We look at a tree and see a label, a category. Rather than seeing the intricate reality of that specific living thing with its particular bark and branches and leaves, we look at the night sky and see darkness with points of light, rather than truly seeing billions of distant suns, each perhaps with worlds of their own. But wonder doesn't have to fade. It can be maintained, cultivated, deliberately sought out, and science is one of the best ways to find it. Not science as a collection of facts to memorize, not science as equations on a blackboard, but science as a way of looking at the world with fresh eyes. Science as a method for peeling back the familiar surface and revealing the astonishing reality underneath. Every new discovery, every image from a distant telescope, every equation that elegantly describes reality, these can evoke wonder if we let them. Consider what science has revealed, that time itself is not absolute but can slow down or speed up depending on motion and gravity. That solid matter is mostly empty space, with electrons orbiting nuclei like planets around tiny suns. That the universe had a beginning and is expanding and will have an ending, though not for trillions upon trillions of years. That life, complex chemistry in action, emerged from non-living matter and evolved over billions of years into the spectacular diversity we see around us. Each of these truths is more wonderful than any myth. The debate over 3I/ATLAS, far from diminishing wonder, actually enhances it. The fact that experts are unsure, that the evidence is ambiguous, that the object defies easy categorization, all of this makes it more interesting, not less. It reminds us that the universe is not a textbook waiting to be memorized. It's not a puzzle with all the pieces neatly packaged and a picture on the box showing what the completed image should look like. It's a living mystery, unfolding in real time, full of surprises and ambiguities and questions that resist simple answers. Think about what we've learned in the process of studying 3I/ATLAS. We've learned that observing distant, faint objects is genuinely difficult, that even with our best instruments and our most careful methods, we can reach the limits of what's detectable. We've learned that different researchers, all skilled and honest, can look at the same data and reach different conclusions based on how they weight evidence and what assumptions they make. We've learned that nature doesn't always cooperate with our desire for neat categories, that some objects sit in the fuzzy boundaries between classifications. These are valuable lessons. They're lessons in humility, in the limitations of knowledge, in the importance of careful reasoning and honest communication. They're lessons about how science actually works, which is often messier and more uncertain than popular portrayals suggest. Science isn't about white-coated figures pronouncing absolute truths. It's about people struggling to understand a complex world, making progress inch by inch, occasionally getting things wrong, always trying to do better. There's a particular kind of wonder in contemplating things we cannot fully know. A distant object seen only as a faint smudge in a telescope, about which we can make educated guesses but never be entirely certain. There's poetry in that. There's beauty in reaching toward understanding even when it remains just beyond our grasp. It's like looking at a painting and seeing not just what's depicted, but also the brushstrokes, the layers of paint, the artist's decisions. The uncertainty becomes part of the work itself, adding depth and texture. This kind of wonder is quiet. It doesn't shout or demand attention. It's not the wonder of a fireworks display or a roller coaster. It's more subtle, more contemplative. It's the feeling you get lying on your back on a clear night, looking up at the stars and thinking about all the vast distances and deep time those points of light represent. It's the feeling of being small in a good way, not insignificant or diminished, but connected. Part of something much larger than yourself. It's the wonder you might feel reading about a single cell in your body, learning that it contains 3 billion base pairs of DNA, an information molecule that encodes the instructions for building you, and that this same molecule, with variations, exists in every living thing on Earth. Connecting you to trees and bacteria and blue whales through a shared heritage stretching back billions of years. You're related to all of it, all life, all the way back to the first replicating molecules in some warm, ancient ocean. Or it's the wonder you might feel learning that the light from a distant star has travelled for centuries or millennia to reach your eye. That you're seeing the star not as it is now, but as it was when that light began its journey, perhaps before your great-great-grandparents were born, perhaps before your nation existed, perhaps before humans had even invented writing. You're looking backward through time, seeing history directly. Science, at its best, fosters this kind of wonder. It gives us tools to look deeper, to see farther, to understand more than our unaided senses allow. But it also teaches us humility. The more we learn, the more we realise how much we don't know. Every answer raises new questions. Every discovery reveals new mysteries. The horizon of knowledge keeps receding as we approach it. This isn't frustrating. It's exhilarating. It means the universe is richer and more complex than we imagined. There's a famous statement by physicist Richard Feynman. He was asked whether scientific knowledge diminishes the beauty of a flower. If you know it's just molecules and cells and biochemical processes, is it less beautiful? His answer was no. The scientific knowledge adds to the beauty. You can appreciate the flower's colour and form as anyone can, but you can also appreciate the evolutionary processes that shaped it, the biochemistry that creates its pigments, the ecology of its relationship with pollinators. The beauty deepens. It doesn't diminish. The same is true for 3I/ATLAS. We could simply note that a faint object passed through the solar system and leave it at that. But by studying it, by trying to understand what it is and where it came from, by engaging with the uncertainty and the debates, we're enriching the story. We're adding layers of meaning. The object becomes more than just a speck of light. It becomes a messenger from the distant past and distant places, a reminder of cosmic processes, a puzzle that challenges our understanding. So as we close our exploration of 3I/ATLAS, let's hold on to that sense of wonder. Let's appreciate the beauty of a universe that includes both the known and the unknown, the certain and the ambiguous. Let's be grateful for the mystery as much as for the solution, because both have value. The mystery invites us to think, to question, to imagine. The solution, when it comes, satisfies one question but always opens up others. Let's be grateful for the scientists who study these objects, not because they'll give us all the answers, they won't, and that's okay, but because they're asking the right questions. They're pushing at the boundaries of knowledge. They're looking up and out and asking what's there, and they're honest enough to sometimes say, quote 26, quote, which is more valuable than false certainty. And let's remember that we too can participate in this wonder. We don't need to be professional astronomers with access to powerful telescopes. We don't need advanced degrees or specialized training. We just need to be willing to look, to think, to question, to imagine. The universe is there, waiting, full of interstellar objects and distant galaxies and mysteries uncounted. All we have to do is pay attention. All we have to do is let ourselves wonder. Wonder is a choice. It's something we can decide to feel. When you look at something familiar, you can choose to see it with fresh eyes. When you encounter something new, you can choose to engage with it deeply, rather than dismissing it superficially. When you face uncertainty, you can choose to see it as an invitation rather than a frustration. The universe doesn't require our wonder. It exists whether we appreciate it or not. But our lives are richer when we choose wonder. We're happier, more engaged, more alive. We see beauty where others see only mundane routine. We find meaning in details that others overlook. We feel connected to something larger than our individual concerns. So tonight, as you drift towards sleep, carry that wonder with you. Let it be a gentle companion. Think of 3I/ATLAS, that small wanderer, moving silently through the dark between stars. Think of the scientist debating what it might be. Think of all the similar objects out there, unseen and unknown, each with its own story. Think of the vastness of space and the depth of time, and let yourself feel small in the best possible way, connected, part of something magnificent, blessed with the ability to know and wonder about it all. We've travelled a long way together tonight. For more than 2.5 hours, we've explored the story of 3I/ATLAS, a small object that passed through our solar system in late 2020 and early 2021, and sparked a debate that continues to this day. We've looked at the observations from multiple telescopes, considered the evidence both for and against cometary activity, examined the arguments from both sides, and contemplated the larger implications of interstellar objects. We've ventured from the specifics of one ambiguous object to the grand scope of the cosmos itself, from pixels on a detector to the Big Bang and the birth of stars. Where we started back at the beginning, with a simple detection by the Atlas survey on Mauna Loa in Hawaii, seems almost distant now. That moment when an automated system flagged a moving object, when a human astronomer looked at the data and realised it might be something special, that was the seed from which this entire exploration grew. But every journey, no matter how far it goes, no matter how complex it becomes, begins with a single step. Or in this case, a single pixel on a detector, a faint trace of light that said, quote, 27, quote. From that small beginning, we've woven a story that touches on observation and theory, on evidence and interpretation, on science and philosophy, on the nature of knowledge and the beauty of uncertainty. And now, here at the end, we return to the question we posed at the start. What is 3I/ATLAS? Is it a comet, an icy body releasing gas as it warmed near the sun? Is it an asteroid, a rocky or metallic object with little or no volatile content? Is it something in between, a transition object that defies easy categorization? The answer, as honestly as I can give it, is that we don't know for certain. We may never know for certain. The object is gone now, racing back out toward interstellar space, growing fainter with each passing day until it's beyond the reach of even our most powerful telescopes. Different experts, looking at the same data, have reached different conclusions. Some see evidence of cometary activity in the form of a possible coma and potential non-gravitational acceleration. They think it's a comet, albeit a weak one, perhaps with an insulating crust that limits outgassing. Others don't find that evidence convincing. They think the coma, if it existed at all, was too faint and ambiguous to be certain about. They think the orbital data can be explained without invoking outgassing. To them, it's more likely an asteroid, or at least an object with so little ice that calling it a comet is misleading. And you know what? That uncertainty is not a failure. It's not a problem that needs to be fixed. It's part of the story's beauty. We're not diminished by not knowing. We're enriched by the attempt to find out. The debates, the careful analyses, the multiple research groups examining the evidence from different angles, the papers published and peer-reviewed, the conferences where researchers present their findings and argue respectfully about interpretations, all of this is science at work. This is what science looks like when it's grappling with something at the edge of detectability, something genuinely ambiguous. The fact that the answer remains uncertain doesn't mean the effort was wasted. Far from it. Every observation of 3I/TLAS added to our collective knowledge. Every spectrum taken, even if it didn't show clear gas signatures, taught us something about the limits of our instruments and methods. Every orbital calculation, whether it showed non-gravitational acceleration or not, refined our understanding of how to track fast-moving objects. The next interstellar object will be studied better, more efficiently, more effectively, because of what we learned from 3I/ATLAS, and the one after that will benefit even more. This is how progress happens. Not in sudden breakthroughs, but in incremental improvements, in lessons learned from both successes and ambiguities. If you've enjoyed this slow drift through space and science, if you found some peace in this exploration of distant mysteries, I hope you'll share your thoughts in the comments below. What did you find most interesting? What surprised you? What questions do you still have? I read every comment, and I love hearing from you. It makes this feel less like me talking into a microphone and more like a conversation, a shared experience of wonder. And if you'd like more of these calm explorations of science and space, topics that are fascinating but delivered in a way that helps you wind down and rest, a subscribe would be wonderful. This channel is a small community of people who enjoy ending their day with curiosity and contemplation, rather than stress and stimulation. People who find peace in learning, who enjoy falling asleep to stories about the universe. You're very welcome here. And I'm grateful for every person who's become part of this quiet little corner of the internet. Wherever you are in the world right now, whether it's late at night and you're tucked into bed, or early morning and you're lying awake before the day begins, or some other quiet time when you need calm, I hope you're comfortable. I hope your breathing has slowed a bit over the course of this long journey together. I hope your thoughts have quieted, that the concerns and worries of the day have faded into the background. I hope your shoulders have dropped, that your jaw is unclenched, that your body has softened into whatever surface you're resting on. Perhaps you've already drifted off to sleep, and if so, that's absolutely perfect. That's exactly what these videos are for. The words continue even after you've stopped consciously hearing them, and that's fine. They're here if you need them, whether you're awake or asleep, whether you're listening intently or letting them wash over you like a gentle tide. But if you're still awake, still listening, still following along, that's wonderful too. There's no wrong way to experience this. You're exactly where you need to be. Look up at the night sky if you can. If there's a window nearby and the sky is clear, take a moment to actually look. Or imagine it, if you can't see it right now. Imagine all those stars, each one a sun like ours or different from ours, each one potentially with planets, with small bodies, with objects that might one day become interstellar wanderers. Imagine the vast distances between them, distances so large they're measured in light years, distances it would take thousands of human lifetimes to cross even at the speeds our fastest spacecraft achieve. And somewhere out there, far beyond our ability to see now, far beyond what any telescope can detect, 3I/ATLAS continues its journey. Right now, at this very moment, it's moving through space at 34 kilometers per second relative to the Sun. Every second, it gets 34 kilometers farther away. In the time it took me to speak this sentence, it travelled perhaps 150 kilometers. By tomorrow, it will be nearly 3 million kilometers farther than it is now. In a year, 1 billion kilometers farther. It doesn't stop. It doesn't rest. It just moves, silently, steadily, following the path that gravity and momentum dictate. It doesn't care what we call it. It doesn't care whether we decided it's a comet or an asteroid. It doesn't care if we understand it or remain puzzled by it. It doesn't know we exist. It doesn't know that for a few weeks in late 2020 and early 2021, creatures on a small blue world pointed their instruments at it and wondered. It doesn't know that people are still debating its nature, still writing papers, still thinking about what it might tell us. It simply is. It simply moves. And there's something deeply peaceful about that thought. The universe goes on, vast and ancient and indifferent to our worries and questions. It doesn't need us to understand it. It doesn't require our attention. And yet here we are, conscious beings on a small world circling an average star, capable of detecting these visitors, capable of wondering about them, capable of finding meaning and beauty in the attempt to understand. We're tiny in cosmic terms, occupying a moment in deep time, living on a mote of dust suspended in a sunbeam, as Carl Sagan put it. But we're not insignificant. We're not meaningless. We're the universe's way of knowing itself. We're the part that looks back and asks questions and feels wonder, and that's something profound, something worth appreciating as you drift towards sleep. In the end, what matters is not whether 3I/ATLAS is a comet or an asteroid. What matters is that it came, that it was seen, that it sparked curiosity and debate and wonder in the humans who noticed it. It connected us, briefly, to the larger galaxy, to the processes that happen everywhere stars and planets form. It reminded us that we're part of something vast and ancient and ongoing. It gave us a story to tell, a puzzle to ponder, a reason to look up at the night sky and ask questions. It gave us an opportunity to practice wonder, to sit with uncertainty, to appreciate how much there is that we don't know, and how beautiful that unknown can be. So sleep well, wherever you are in the world. Let your eyes close if they haven't already. Let your breath deepen and slow. Let your thoughts drift like clouds, present but not demanding attention. Dream of distant stars if you dream at all. Dream of objects travelling through the darkness, bearing stories we may never fully know. Dream of scientists in observatories scanning the sky for the next visitor. Dream of telescopes and spectrographs and orbital calculations. Dream of the beauty of questions without answers, of the quiet joy of wonder, of a universe richer and stranger and more magnificent than we can fully imagine. And know that somewhere, always, there are people looking up, asking questions, seeking understanding. People who devote their lives to studying the cosmos, not for fame or fortune, but because they can't help it, because they're driven by curiosity and wonder. You're part of that tradition. Whether you're a scientist or simply someone who looks at the sky and asks, quote, 28. You're part of the ancient human impulse to wonder, to question, to seek meaning in the patterns of stars. Good night. Rest easy. Let the day fall away. Let your body relax completely. And may your dreams be filled with stars and mysteries and the gentle certainty that the universe, in all its vastness and complexity, in all its ambiguity and wonder, is a place of profound and endless beauty. May you find peace in not knowing, comfort in uncertainty, and joy in the eternal questions that make us human. Sleep now. Dream of small wanderers crossing vast distances. Dream of light travelling for years to reach us. Dream of telescopes waiting patiently for the next visitor. Dream of debates conducted with respect and passion. Dream of a universe that doesn't need our understanding but is blessed by our wonder. Good night.